Okay, welcome everyone to this Magma Mondays or introduction to Magma. So we are running this, well, me and Don Taylor, organized by these guys here. So by Bregje, Pauwels, and Alexander Sherman, Alex. So we are running this Magma lecture, and there's a really beautiful website Alex has set up. And the goal is to explain Magma to a more general audience so that you can use it as a computer algebra system. I kind of explained that a little bit in the previous video. And you can use it in your own research because it does exact calculations or for your thesis or whatever. So you can literally just do calculations and put them in your thesis or in your paper or whatever, or you can use them as a guide to get conjectures or something like that. And I did that in the past, like several times. I'm a really large Magma fan. Magma is not optimal, it's not perfect for everything, but kind of for algebra-ish things, it's kind of really great. So I usually really like to use it a lot, and the whole point of this lecture is to get you kind of started from scratch so that you can do some of your own work. And so this kind of, I'm just following the lecture notes. So if you go to the website, which is also linked in the description, of course, you will find the previous videos. So actually, I'm re-giving Don's talk, so you can also find the lecture notes or the videos here for the various lectures. And the reason why I like to re-give the talk is, well, certainly I will do it slightly differently, but using the same material. So the material is all due to Don. And I would like to again highlight the usage of the online calculator. So if you go to the website, and maybe that's kind of fun to do it live with me. Well, for you it will be live, but for me it won't be live because this is obviously recorded. But anyway, you can do it live together with me. So if you go to the website, you will find the lecture notes. They're also linked in the description, and you can open them. And I just did that, and that's what they are. And we will just run everything directly in the online calculator. So my whole point about Magma is that it's somewhat you can just start right away. You don't need to install anything. It's really, really fantastic. So the way to find the online calculator, well, there's a link on the website. Another way of doing this is just type in Magma, use SID, because otherwise you will find University of Sydney, it's run by University of Sydney by use SID. If you just find Magma, you will find, well, let's do it. You will find pictures of Magma, I guess. That's what you will find. That's not what I'm interested in. I'm interested in the one you get from SID. You will find it. It should be the first hit on Google or whatever kind of search engine you use. This is a website, and they have the online calculator here. And that's the one we are going to use. Let me just zoom in a little bit. So that's a bit easier to see for you. Okay, so you can just paste everything inside here, 3 + 4, and whatever. We'll get the answer 7. We did that already in the previous lecture. So obviously during those lectures, I kind of assume that you have seen the previous one. So maybe if this is your first video on Magma, maybe this is not the right place to start. You should go back to the website. Or actually, you're watching this on YouTube, maybe you can go to YouTube and just go back in the playlist or something. You're smart. You'll be able to figure that out. Anyway, so what we do now is we pull up the lecture notes and we go through some ideas what Magma can do for you. So the lecture 1 is section 4 right now in the lecture notes, and we're going to do that. And I skipped section 4a. So if you want to know 4a, go to Don's talk, Don's video. I'm skipping it because that's the only part of the whole lecture note that does not run in the online calculator. It loads an additional file. That's what an online calculator can't do. So I'm going to skip that. Fine. Okay. But what I want to do is I want to kind of discuss a little bit recursion. That's kind of the first thing I want to do, because recursion is kind of really exciting. It's really good. Magma loves recursion. It's really fantastic. And kind of the easiest recursion would be probably the factorial. But let's do it something more sophisticated. Let's try the Catalan numbers. Okay. So here's the definition, well, if you want. It's not really the definition, it's just a formula for the Catalan numbers. Kind of an easy formula, and we can just run that in Magma. Just what you need to do is you just need to grab this, you copy it, you paste it in the online calculator, and it will tell you whatever, the result. So diff here is integer division. So let me just do another example with diff. If you do this one, for example, it kind of drops the remainder. It's really integer division, right? So, but anyway, let me put in this one again. Whatever, some large number. And Magma can handle large numbers like really quickly. So yeah, so that was pretty good. By the way, you don't need the print here. It will do kind of the same. So this all. Great. So the Catalan numbers, they count bracketings. Like in this case here, fifth Catalan number, we'll see that in a second, is the fifth Catalan number. The fourth Catalan number is 5, and there are 5 bracketings of 4 symbols. That's exactly what it is. And this kind of idea, that's what I want to stand here. Okay. Okay, so that's the Catalan numbers, and that's a very explicit formula, but sometimes it's nice to have an asymptotic formula, and there's kind of a well-known one, which follows immediately from Stirling's approximation. So the Catalan numbers, actually, they grow like 2 to the 2 to the n up to some correction factor involving the square root of pi. So kind of in Stirling's approximation, you always hit the square root of pi. Here's the square root of pi. But you can already see it grows like really fast. So this is the dominating term, 2 to the 2 to the n. And to set that up in Magma, so let's first do something that's a bit confusing. So Magma usually does exact calculations. So it more prefers rational numbers over real numbers, for example. So you kind of need to set up real numbers. So pi is the number pi in the real field, and 10 is the position, so the number of digits you will see. So 3.14 whatever, and there are 10 digits. Okay, so I could go to 20 if I want to, and then there will be 20 digits. Okay. So that sets up pi. We're again setting up pi, and then we can do the following. We just set approx cut. Cut is for Catalan numbers, is the following thing. Approx cut is a function. So Magma knows functions as function. So it has an input n, and it has an output exactly the approximation formula. And we can just do that. We don't need the print here. We can do it with a print or without a print. And it will let me not display pi, and it will output the approximation of the Catalan numbers given by this funny formula. And it will be some real number because you have a square root of pi. Good. That's all good. But note here that I set up precision 20, right? So that's the total number of digits, not the number of digits after the dot, right? So it's really the total number of digits. So here I have 10, but only have 2 behind and 8 in front. So if you want a lot of precision, I don't know, set something like 100. But it's kind of really easy, and I have to highlight this function, which is exactly what you think it is. During takes an input and is a function, right? It's a function in the classical sense of algebra. It's kind of the standard function and expression. Right? You can set up more variables if you want, but yeah, that's what it is. I hope that's hopefully reasonably clear. But this is an approximation, right? And I was just selling the idea that Magma does exact calculations. So how do we do an exact calculation for the Catalan numbers? Well, you could do this one here, sure, fine. But from the definition itself, this formula is actually not so obvious. But what is kind of clear is the number of bracketings can be counted by number of certain bracketings to the right. You kind of take the biggest bracket and put them to the right, and then have some remainder on, put them to the left, and you have some remainder on the right. So you actually get this recursion here for the Catalan numbers. And I will now tell you how to set that up in Magma. So let's do this. So we copy this and we put it here. Okay, so nothing will happen. So this is somehow misplaced. Nothing will happen because I just set up the function itself, and you would need to ask it whatever, Catalan sequence number 5, for example. And it displays, in this case, it doesn't display the 5th Catalan number, but it will print out all Catalan numbers as a sequence up to that point, which kind of makes sense because it's a recursion, so it calls itself anyway. We'll explain that in a second. So it kind of makes sense to have a little bit more of an output than just a number. You can adjust that to have just a number as an output. Okay, what's happening here? So function n is just, okay, it sets up the function, and here's the n function. If n is equal to 0, okay, 0's Catalan number is 1, fine. If n is equal to 1, well, we just display the first 2 Catalan numbers, fine. And otherwise we call a recursion. And the recursion is called as follows, with the double dollar symbol. Whoa, that's a mouthful. Double dollar symbol. So the double dollar symbol just say, call yourself with the following value. So call the Catalan number with a smaller value in that sequence, and then you can do just exactly the recursion that we were on the slides. Right? You just do the recursion in the Catalan numbers, and well, then you return the sequence. And because I'm printing, I can take out the print sequence, and so we'll see what happens. If I take out the print sequence, that's why it prints out everything. If I take out the print sequence, I just get the final result. But the point here is the recursion, so the function calls itself using this double dollar, right? And this is mimicking exactly, and what is written here is then just mimicking exactly this recursion. And it's really good. So recursions are fantastic. They're breakfast for machines. Machines usually like recursions. It's usually a bit faster to program something recursively than like with a for loop or something. Okay, so if you can do a recursion, do a recursion. Right? And here's it explained actually what is happening. Okay, but let's come back. So this one is a lot of fun. So let's just copy it and see what happens. I need to copy it because of the line break in 2 steps, but that's fine. We survive me copying this in 2 steps. So this one defines a procedure. Okay, procedure has no output. So I generate an output by printing whatever. And it's essentially the idea to generate a random bracketing. It's kind of a bit tricky to run because it picks a random element, and then depending on what that element is, it either kind of makes some random thing shorter or longer, and it does that until a certain point. And what you get is something like this, right? A random bracketing, and that's exactly kind of matching some of the Catalan number things. So this sequence somehow generates the Catalan numbers as brackets, which is kind of nice. And I kind of leave it to you to explore what's going on. It's not so difficult. The main meat here is this part, which kind of depending on a random input, does something. It either inserts something or removes something. And let's do it again, because it's really random. So abs is the empty symbol. It's really random, right? If you press it several times, you get different results. There you go. So it's a random generator. And I would like you to just read it and try to understand it. It's a little bit of an exercise. It's not so difficult. The main meat happens here in the repeat until. Repeat until. Yeah, and then I just print the result. The rest is not that exciting. Okay. So this was my part about the Catalan numbers. So what we have seen, let's scroll back, is actually this recursion, which I wanted to sell because recursions are like really, really important. And the main symbol for it is a double dollar. There are different ways of doing it, but let's just focus on the double dollar. Awesome. Okay, so let's move on. And there are a lot of exercises with really, honestly, you learn a program language. Practice makes perfect. It's true for everything. And for programming languages, it's even more true. So if you really want to learn this, it's probably not fun, or whether it's fun or not, doesn't matter. It's probably not very efficient to just watch me talking, but it's just probably boring anyway to watch me talking. Who wants to watch me talking anyway? Anyway, so I really recommend to try to do the exercises. They're hopefully not so difficult. If you have any questions, just let me know. You're free to shoot me an email. Okay, so let's do, the rest is essentially about group theory. I would like to tell you about group theory. So the whole point about these lecture notes is that if you are, whatever a grown-up mathematician is, you should be able to kind of read everything. Everything should be relatively self-contained. So we are not assuming that you know what a very difficult thing is and then run it in Magma, but Magma could do those as well. So we kind of stay with easiest examples that hopefully you have seen in some way or form in maths. In particular, I would like to look at the Fano plane. Fano plane, which is the projective plane of a certain order. So if the projective plane is finite, then the order is always n such that there are n squared plus n plus 1 points and n squared plus n plus 1 lines. And our friend Magma already knows the Fano plane. It's just a finite projective plane of order 2. So there are 7 points and 7 lines. And let's just output it. There you go. It doesn't give any output, so I could just say, what is Phano? What is Phano? It's a projective plane. There you go. What is P, with points in Phano? Well, there are 7 of them, and they're written in homogeneous coordinates. So that's a projective plane. And what is L? Note that this is here an ordered set. That's what it is. L is corresponding to the number of lines. There are also 7 of them. Okay? So the lines in this. So we can also output them like this if you want, instead of outputting the whole set, because they are ordered. They're ordered sets. So I can ask it to give me the second element or the third element. Right? I can just do that. And I can ask whether P is in L, for example. Is that point in L? Yes, it is, and so on. So all that stuff, I can do that with our Phano plane. And this guy had 3 outputs actually, which is the plane itself, at the points and the lines. That's what I just did. Phano plane. And now a flag in a plane is a pair of point of the line such that the point is in the line. So a flag would, for example, be this line and this point on it. Right? So this line has 3 different flags associated to it. 1, 2, 3, by choosing any of those points. And I want to create a graph in Magma just for fun. Why not? That does the following. It has some additional start vertex, which I call star. Completely unimportant shit. Forget it, but I just add it. Okay. And I join it to P and L. Fine. So all points and all lines. And I'll join all points to the 4 lines not through it. A little bit annoying. To the 4 lines not through it. So this point here is not joined to this line, to this line, to this line, and to this line. The 4 lines not through it. Fine. And we join the points on 9 flags to their 9 flags. We join the 9 lines to their 9 flags. So why does a point has 9 flags? What would be those flags? Well, it has 3 lines that it lies on, and every line has 3 additional points. So there are 9 flags that it lies on. And then we join the flags if they have kind of this funny property that the point lies on the other line and the other point lies on the other line. And you will get a graph, and we'll see what that does. It will look like this, but let's see how to do this in Magma. Okay, so let's set this up. And it's a bit, well, let's do it. So we keep this one. We keep the projective plane. So the vertices, my star vertex, I just call it 0, 0. Wonderful. The first are 7 vertices. They should be the points, which I call -1i. So -1 stands for points. The next are the edges, which I call -2. So -2 stands for points, and the second one runs from 1 to 7. And then are kind of set up the pairs. So this just sets up pairs. The flux, because I and J, but there's a condition that Pi is in Lj. That's exactly setting up the flux, right? Okay. Let's just do that. Let's call that thing the flux. And then set up the whole graph is the following. And it's really just mimicking, just read it, right? It's a little bit boring to explain what is going on, but it's really just mimicking the procedure written up upstairs. And then what you can do is now you've set up all sets and you just need to collect them in a graph. And in Magma, you do that the following. It has 3 outputs. And I just do it this way, maybe. It just had 3 outputs, which is not bookmarks, which is the graph itself, the vertices and the edges. And it just graph vertices and edges. And what I did here upstairs is I set the vertices by join, join, join. These are all the vertices. I set the edges by join, 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 right? So I've set it up everything. So this should be the graph. And I can ask what is the adjacency matrix of a graph. And it's a fabulously large beast. Okay, that's what it is. So what you can do, I kind of recommend to do that. If you just have a look at a really beautiful web page, it's called Graph Online. So let's copy the link address. Let's put it here. So Magma is not really disadvantage of Magma is that it's not really good to output kind of graphical kind of output. So it's a bit annoying. It gives you the adjacency matrix. So what I usually like to do is grab that matrix and put it in this online calculator, you can just do it as follows. You can just give it an adjacency matrix, and it will create a graph for you. So as you can see, the graph is reasonably complicated. Yeah, so that's the graph. I also created it here in the file, a bit complicated. So let's do it in a slightly easier example. Maybe I just open another tab. There you go. And we just do the Peterson graph, which is much smaller. So you can also set up so the whole point of the previous one was to illustrate that you can set up large graphs. You can also set up small graphs just by hand. So 10 vertices, they're labeled 1 to 10, join 1 and 2, join 1 and 5, join 1 and 6, and so on. And you get some adjacency matrix, fine, that you can just copy, and you get a much nicer looking, let's get rid of all that shit. A much nicer looking graph. It's much smaller. And let's see what we can actually do here. Arrange the graph algorithm. And it's not so bad. This one is not so bad. It's not as nice as a Peterson graph is supposed to be. The Peterson graph is actually this object here, which has this nice presentation. If you draw it correctly, if you don't draw it correctly, there is no wrong drawing, but it's the same graph. You can check that. Anyway, the whole waffle that I just had is the following. So you can set up graphs in Magma very efficiently, and Magma is fantastic with graph algorithms, but it's not so great to illustrate them. And what I usually like to do is to use some other software for illustrations. You can also copy that in Mathematica or something and just illustrate. Anyway, what Magma is really fantastic is it has so fast algorithms that it can compute stuff with even large graphs. So this graph is large, yeah? This is hopefully clear that the graph is reasonably large. So let's get rid of the adjacency matrix. We've set up the graph, and we can ask it for the automorphism group of that graph. And let's just output the automorphism group first. What is the automorphism group of that graph? It's a group of, it just took a second, right? It was instant. It's a group of order 12,000 whatever. And Magma displays it as a subset of the symmetric group S36 by just displaying the generating permutation in that subgroup. So whatever that is, fine. And it took it an instant to do it. Magma is just absolutely fantastic. It's a super large graph with a super large automorphism group, and Magma just did it in an instant. I hope this is kind of reasonably clear. So automorphism group, and what we can do is we can try to identify it. We can ask properties of the automorphism group. Is it transitive, for example, or even nicer, we can just ask composition factors, and it's a large group, and Magma will just do this super fast. There you go, you have the composition factors. So there's a ZMod2, a cyclic group, and then it's essentially this is notation from the table of finite simple groups. So if you know the Atlas notation, it's a type A thing. It's a unitary group 3-3. There you go. It's actually not so difficult. And Magma does that in a second, and now you've identified the group up to a ZMod2 factor. It's really just the unitary group 3-3. It's kind of really impressive that Magma can do this so ridiculously fast. So here's again A. And Magma is just, I mean, it's ridiculous, right? It just takes almost nothing. So we can try that. To do that, if we just add time, then it tells me I needed 0.00 seconds, so it was instant to do it. And that's for a group of order 12,000 something you don't do by hand. And you could still put this result in your thesis, or whatever, composition factors, in your thesis or factors, I guess, in your thesis or your paper or whatever. And you just have identified the group without doing any calculation by hand. It's really nice and very impressive, and just super efficient. So I'm big, in case you couldn't tell, I'm a big fan of Magma. Okay, so let's have a look a little bit more about finite groups. And I want this property, something you can do live. Just try to solve an open problem. I mean, what I'm going to show you is not an open problem, obviously. But you could do that, kind of generate a list of counter examples or something like that. And that's what you're going to do now, because Magma has also access to databases, which are really large databases. So I call a group or a set product free if you for all AB, the product is not in the set. So let's just give an example. Let's get rid of the fatal plane. Okay, so the function here just sets it up, fine, and it just does whatever. It's not really difficult. So let's test the set 2 and let's set the set 1 2. Okay, submit. The set 2 is product free. Why? Because 2 times 2 is 4. Huh? So there you go. It's not in the set. The set 1 2 is not product free. Why? Because 1 times 1 is 1, and that's in the set. Huh? I hope this notion of product free is reasonably clear, right? So let's do 2 and 3. So what about 2 and 3? 2 and 3 is true because all the products are not in the set yet. Does it make some sense? I hope that's not too difficult. And now we write a function which is called checkmax, and it kind of finds all groups or tries to find all groups, or actually returns true or false depending on the group for all product-free groups. With product-free sets of sizes 1 in this case. Maximal product-free sets of sizes 1. I leave it to you to explore the function. It's not so difficult. There's a for and the if, but let's see what it does. So right now it doesn't do anything because I guess copied it wrong. I forgot the end function. Yeah, so it just tells me, oh, by the way, that can't work. Whoop. And fine, good. And now let's run the function. For example, we can do the following. We can just run through all cyclic groups. Yeah? Cyclic group n for n from 2 to 10. So cyclic group 2, 3, 4, 5, 6, whatever. And it gives us a list. True, true, true. False, 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 false. We can go a little bit further. False, false, a lot of falses. So you might make a guess at this point that for cyclic groups, the answer is true for n equals 2. For the z mod 2, z mod 3, and z mod 4, and then it's wrong. That would be my guess at this point. What we can also do is we can run it for any group Magma has built in naturally. So for example, the dihedral groups, you run it, the dihedral group, whatever, you just copy it from the oh, that's a problem. Okay, why doesn't it like it? Because the dihedral group starts indexing at 3, so the dihedral group 2 doesn't make sense. Fine, let's do it for the dihedral group, and it will return in an instant. Let's do it again. Time, this beast return in an instant that everything is false. Not quite an instant. It's a half of a second actually. That's pretty slow, Magma. I'm a bit disappointed. You should be able to. Well, I don't know, but anyway, it's much faster than if I do it by hand. Okay, all is false, so you might conjecture that for the dihedral groups, the property is just always false. And it's kind of exciting because this is how you could use Magma in your research. You just generate some examples and then you have some conjecture and you can just go and prove that conjecture. So let's generate more examples. For example, what you can do is the following. It's kind of really nice. So Magma has small groups built in. Okay, so we can do, for example, the number of small groups of order 32, and Magma will say there are 51 groups of order 32. Okay. Very good. So what you can do is you can access them as follows. So you can access them as follows. So 32 is still the same. And I take the third group. So it listed, they list all of them. And I take the third group by just saying small group, order, number on the list. And well, that's what it is. It's a group given by, funny output here, G1 as a generator, G2. So G.1 is just the first element in this beast. G.2 is the second, G.3 is the third, and it has a relation that G.1 squared, for example, is the third element, and the second generator squares to the fourth element, and so on. So these are the relations in the group, and it has order 32. And we could access others like the second one, or the first one, or the sixth one, or whatever. No, so something like that. And it knows all of them. It's kind of exciting, and you can go to much larger values. If you want, well, there you go. And there's some group. And with a reasonably, well, with quite a long list of generators and relations. But anyway, so it knows a lot of those groups, right? So this is the output here. So there's a small group database, which we can just note just for efficiency, but let's not do it. We don't need to do it. Okay, I need to copy this one and then explain what it does. Let's get rid of this guy. Good, and I have an N4 missing at the end because it was on the other page. So let's add that one again. So for N from 2 to 50, do for J1 to the number of groups of that order, do pick, so it goes through all of them. Pick the NJ group, so just go through all of them from 2 to 50 and print the witness for whenever this property is true. Okay. So we're now running through all groups up to order 50, and we'll see how long that takes. Yeah, so N4, and we just printed, and it runs a little bit, but it wasn't so bad. So it says there's one group of order 2. Yeah, one group of order 2, and the witness is this element. There's one group of order 3, and there's one group of order 4, and there's there's a group of order 2, 3, 4, and 8. Okay, and it's the first group on the list. If you do this list here, it's first group on the list, it's first group on the list, and it's the fourth group on the list. We already know those guys. These are just the cyclic groups. So we only need to identify this guy here, which is this group. So G defined as, we can now get rid of all of this. Pull up the group. Yeah. So remember, it's the fourth one on the list. Let's just pull it up. You can copy it, pull it up. Small group 84. Which one is it? Is it abelian? For example, we could ask that. It's not. So it's one of the 2 other non-abelian groups. One of them is not encoded in Magma, which is a bit of annoying. And it is exactly that one. So let's try to find it. So it's not abelian. Fine. So which one can it be? Well, let's output it. Let's see how Magma thinks it looks like. There you go. It's a non-abelian group with 3 generating relations. Okay, that's what it is. What could it be? Well, let me just set up the standard notation for the, what is it, the quaternionic group. So this is the quaternionic group. It's a bit annoying because it's not included in Magma. It's a bit annoying, but anyway, this is the standard presentation of it, and we can ask whether it is actually isomorphic, and it's true, and it's even better, it will return an isomorphism of 2 to my given group Q. So it will return my isomorphism. In this case, it just says 1 to 1, 2 to 2, and 3 to 3. But anyway, you can check whether 2 groups are isomorphic with each isomorphic, and it will even return the isomorphism. So you have now kind of a solid, essentially we now have a solid conjecture. Let me pull it up again. What this, here was our list, what the product 3 groups of maximal size 1 are. They're probably only 4, because we checked up to groups of order 50. You could go much further if you want to just take a bit more time, and you will get a solid conjecture that these are the only ones, and then you can go and prove it, which is kind of the whole point I'm trying to sell today. Right? And there are several exercises related to it. So let's end with another recursion for today. Let's do the Knapsack problem. So the Knapsack problem is the following. We have a Knapsack, let's say a number like 151, and you will want to fill it up with primes, with different primes. So what do you need to do? So here's a Knapsack function. You just copy it as efficiently as possible. You want to fill it up as efficiently as possible, and it will call itself. That's kind of a fun exercise to try to understand what it does. It fills up 151 with those primes, which perfectly sum up to 151. By the way, this is a bit silly. So because there's a conjecture that everything is a sum of 2 primes, and I'm filling in a lot of primes, so we'll always get this number here. So we'll always get the correct number, but it somehow gives me primes that sum up to that number, if you want. But we can modify that. So let's still call the set primes, but maybe we just want it to be I squared for I in 1 to 100, and we do the same. And of course, I should not do I squared and then P in 1 in 100. That is not supposed to work. So let's do it this way. And this is a little trickier, as you can see. So you're trying to fill it up now with square numbers. We could try cube numbers if you want. You could fill up the Knapsack with cube numbers, and that doesn't work. And I have no idea why, actually. So let's go back to square numbers. this should actually work. I'm confused about the error. Illegal null sequence. Oh, in this case, there is nothing. There you go. There's nothing. That's weird. So let's output it. And indeed, there is nothing. Okay, fine. Let's do it again. And we can output $+K. So in this case, it's sum up perfectly, but maybe we want to change our little output to 150, where it sum up perfectly. And there was a solution, and there was a solution, and there was a solution, and so on. So let's do that with cube numbers. There's no solution. Very interesting. There's no solution. Ah, there's a solution. 153 is actually a sum of cubes. And you can see that gets way more interesting, and the Knapsack problem gets way more complicated. Whatever. I have no idea which one is a sum of forced powers. Maybe we should do something like the following. For J in 1 to 10, do plus J, something like that, return K, and then end 4. We're doing this live now, so there's a chance that this goes wrong. Nothing. So there are apparently not many numbers that are sum of whatever, the forced powers. So maybe let's go ahead a little bit further. Okay, there was one. Hey, fantastic. And I guess it's just the forced power itself. So this probably gets way more interesting if you just vary the input set here. So here, 2 works very well. 3 doesn't work that well, as you can see, not many, or whatever. You can vary the problem, of course. And I leave it to you actually to vary the problem. Anyway, that was my lecture for today. So we have seen recursion. I was setting up graphs, and then do some small group calculations. And then kind of a fun problem for you to explore would be, well, how does the Knapsack code actually work? What is it doing? Yeah, and that's how we go along. I present you examples, and the whole point is to kind of take the examples, see what they do, and then modify them to whatever you need to do, right? So that's kind of the whole point. And that's roughly how I learned Magma as well, which might not be the most efficient way of doing it, but that's what I do for this lecture series. So yeah, but whatever. If you don't like it, you don't need to watch the videos, obviously. But hopefully it will be really useful, because Magma, I said again, I know I sound like a broken record. Exact calculations, you can do that. You can run conjectures, you can generate conjectures, you can put calculations in your thesis or whatever. It's really great, really powerful. Anyway, I hope you enjoyed this video, and I also hope to see you next time.